Well, hello, welcome to week 6. So last week, during week 5, we discussed the complexity of functions from the perspective of a circuit-based model of computing. Now, most often when we're measuring the complexity for these circuit implementations, we're concerned with either the number of gates contained in the circuit or else the number of layers that circuit has. So this week, what we're going to be doing is we're actually going to be moving on to our second model of computing, which is that of finite state automata and regular expressions. Those two are equivalent to one another. We'll discuss that further. But before we moved on, I wanted to sort of mention some extensions of topics related to this circuit-based model of computing. So we've discussed this model of computing mostly as an idea of what computers could do if they didn't really have any memory. And as we discuss further models of computing, what we're going to see is that the main thing we're really changing from one model to the next is how much memory we have and what kinds of memory we actually have available to us in our model of computing. So what we're going to see is that there's sort of this overall idea that memory is really what makes computing sort of complicated. And there's some ways that that's going to be a good thing that we've made it complicated, and sometimes it's going to be for the worse, actually. So I just wanted to mention a few different application areas where if you were really intrigued by this idea of a circuit-based model of computing, these are areas where sort of this model of computing is going to be pretty relevant beyond the scope of this course. So if any of these areas particularly intrigue you, then I do encourage you to reach out to find more information about it. So you can either send me a direct message in Discord, send me an email, or just stop by my office hours or professor hangout to discuss these further if you're interested. About where the circuit-based model of computing could be used is actually in something called formal verification. So I have a family friend who used to work for NASA, and with NASA, what he worked on was formally verifying code. So NASA had software that was running their space program, and they wanted to be able to make proofs to guarantee that there were no errors in their software. So they knew a software error wouldn't cause one of their space shuttles to crash or something like that. So what my family friend had discovered while he was working on this was essentially that the big problem in trying to formally verify whether or not there's some bug in your code is the memory. So the fact that you could have these data structures like lists, arrays that have an unbounded amount of memory available to them really becomes a problem when you're trying to make any sort of general assertions about your proof. So or about your code. So what they found was that if you can assume, or if you can ignore the memory, or if there isn't any memory that your program is going to be using, then it becomes really, really easy to prove things about your program. Which sort of suggests that if you have some sort of safety critical system and you're able to consider that system as a finite function, then implementing it in that way is going to make it easier for you to make guarantees about that code. Another example where this can sort of where the circuit-based model of computing can pop up is actually when you're looking at parallel computing, and in particular when you're doing like theoretical analysis of parallel computing. So you might have heard of this class P, and if not, then you're definitely going to hear about it by the end of this semester. But essentially, this class P is meant to refer to all of the problems that a computer can solve efficiently. One shortcoming, though, of this class P is that it really assumes that you're only going to be using one computer. So it's sort of the problems that you can solve efficiently with a single computer. However, like oftentimes when we're actually doing computing today, we're going to have multiple computers working in tandem on the same problem. So, for example, your CPU probably has like 2 or 3 or 4 computing cores, meaning that you have essentially multiple CPUs in your one device that can each be working on different things in parallel. Or when you put some sort of computation on, let's say, Amazon AWS, then you can actually have a collection of computers all working on that same thing kind of at the same time. And when you have multiple machines that are working on that same problem in parallel, sometimes they can cause that problem to be solved a lot faster than you could have before, and then other times it maybe doesn't make so much of a difference. So maybe what we want to do then is we want to be able to sort of formally categorize the functions that are going to be, that we can accelerate by spreading that computation across multiple computers. So we want to have something that's similar to this class P, but for efficiently parallelizable problems rather than just by things that are efficient to solve by a single computer. And it turns out that the most common way that people discuss this category of problems that can be efficiently implemented is by representing the functions that we might want to compute actually as a circuit or as a collection of circuits. So the circuits, by analyzing a circuit representation of that problem, we can actually get an idea for how parallelizable that problem might be. Another sort of similar thing that we might look at is special hardwares or special architectures for computing problems. So if you've heard of something called the von Neumann bottleneck, so John von Neumann, it was a famous mathematician, computer scientist who came up with sort of the high level idea for how our architecture works, that you have some sort of computing unit like our CPU that sits beside some sort of memory device like your hard drive or something like that. And as a result of this architecture, we have something that we call the von Neumann bottleneck, which refers to this idea that accessing memory outside of your CPU takes a lot more time than actually doing computations with that memory inside your CPU. So oftentimes the time that's spent sort of reading and writing to and from memory is sort of the bottleneck in you computing whatever your goal was. So one approach for how we can get around this is by looking at different ideas for how we can actually build our computer hardware. So there are specialized hardware devices that can do some of this work without actually doing memory accesses at all. So one example of this is something called an FPGA, which stands for Field Programmable Gate Array. So that word gate in there does refer kind of to these Boolean logic gates that we have been discussing so far. And essentially what this device is it's a reconfigurable hardware for implementing circuits. So you can put some circuit on there, on this hardware, and it can directly execute that circuit in the hardware, and then later on you can reconfigure it to start working on a different circuit instead. So you can encode it to sort of evaluate one circuit at a time, and because it's now using circuits, it has no memory accesses at all, thereby avoiding the entire von Neumann bottleneck. So this is another case, another situation where thinking of something as a circuit can actually help you to compute it more effectively. And then the final one that I wanted to mention was something called secure multiparty computation, which is this idea in cryptography where what you're trying to do is you're actually trying to allow two people to compute some function on some secret information that they have. So they have some function they want to compute where each person contributes the input to that function, and both people want to know the output, but without needing to give away any of their input to the other person. So a classic toy example of this might be that if there's like a man and a woman who meet at some sort of party and they want to know if they're compatible, maybe what they want to check first is whether or not their hypothetical children might have predisposition to some genetic disorder. So what they're going to do is they want to compute some function on their genomes to see if there's susceptibility to some sort of disease. But they're not going to want to give away their genetic code to the other person in order to do that. So this secure multi-party computation allows for them to compute on their genomes without needing to divulge their genetic code. And the most common way to achieve this is using something called a garbled circuit. So here we have the word circuit there because it is exactly these Boolean circuits we've been discussing. And essentially what these garbled circuits do is it creates a circuit that's going to compute the function, but it's going to do so in a way that sort of obscures what's actually going on so that it's hard to reverse engineer what the inputs might have been for that circuit. Now, one really interesting aspect of this particular application is that just due to some quirk in how the technique works, XOR gates are actually super cheap in this, whereas things like AND gates are going to be much more expensive. So when we're looking at the complexity of our circuits, what we're actually going to do is we're going to be considering XOR as free. So XOR gates we don't count at all when we're looking at the efficiency of those circuits. And instead we're going to say, like, well, how many AND gates versus OR gates were there? Those are the things that we care about. So when we try to design the most efficient circuit that we can, we want to sort of minimize the AND gates, even if that means producing a lot of XOR gates as part of that. So one of the things that I hope that you see by the end of the semester is that each of the several computing models that we're going to discuss is going to have some advantages and disadvantages. And it's not really going to be the case that when you have a more powerful computing model, that is going to be a more useful thing, or just a better computing model. So there could be some advantages to actually sticking with a weaker model of computing when you can, for instance with the von Neumann bottleneck or something like that. So I encourage you, as we introduce our next computing models and as we introduce more computing models throughout the semester, to actually consider some of these trade-offs. So to think about, like, where is this new model of computing better than the ones that we've discussed before, and where are the ones that we have discussed before going to be better than this new one. And that's really going to help you to get a better and deeper appreciation for the theory of computing and for the importance of having different computing models. So I hope you enjoy.